Yes, perfectly. Thank you.
You want to take my seat because I'm actually. Right, so before diving into Uniruled format of course, so let me actually continue with the theme maybe yesterday. I was discussing the classifications of symplectic Calabi-Yau four manifolds. Right. You see that we have made some progress towards that. There's a proposed smooth classification. So there is a very concrete list of symplectic Calabi-Yau surfaces we're trying to prove. On the other hand, if I look at higher dimensional symplectic Calabi-Yau, so this just means symplectic manifold where the first chain class is 0. So actually for four-dimensional situation, we interpret this really loosely. It could be just 0 in the real cohomology rather than the integral cohomology. So we allow a Rick surface in the list because this is sort of like the only exception, and the approach is the same. So here, what in general, this is our definition of symplectic Calabi-Yau manifold here. I mean, I also use the notation K omega. That stands for the symplectic canonical class, but then the C1 here is the negative canonical class. All right. So I was working on this classifying symplectic Calabi-Yau surfaces. So I proved particularly this bound. I mentioned it yesterday. This bond is very meaningful because in the Kähler case, Calabi-Yau manifolds have Ricci flat metrics. So by the Weissenbach formula, any harmonic one forms are parallel. So you can just at most have two dimensional parallel vector fields, right? So for Kähler manifolds, the Kähler Calabi-Yau manifolds, we have this bond. By solution. Calabi, the existence of a Ricci flat metric in this case. So I was hoping that this is such a bond persists for symplectic Calabi-Yau manifold, higher dimension. But soon after, you'll find the Panoff came up with some very general constructions of symplectic Calabi-Yau manifolds in dimension 6 and higher. In particular, they can show the following: given any finite presented group, there exists a 6-dimensional symplectic Calabi-Yau with pi 1 given by G. So this is very similar to Gauss's result in dimension 4. Any finite presented group, you can construct some finite 4 manifold with pi 1 is the given group G. But here, if you impose in dimension 6, you impose the similarly very strong condition being symplectic Calabi-Yau, you can find one. So there's really particularly B1 can be arbitrarily large. No such bound exists, even starting in dimension 6 for a Calabi-Yau manifold. So there's no chance to classify them. And well, maybe I can say a few words about the construction. So it's the tracer space construction on 4-dimensional orbifolds. The very specific kind of hyperbolic orbifold. So assembled from right-angled I'm just throwing words. So myself, I'm not familiar with this construction. It's very concrete, explicit construction. And you're taking the tracer space, such a Riemannian 4-dimensional manifold. Of course, this is not smooth because the base space is orbifold, so the total space is not smooth. And you smooth it by taking a Krapin resolution. Krapin resolution meaning that actually the total that tells you the total space is has trivial C1. So this construction, of course, sort of similar to the construction of hyperkähler manifolds yesterday. You take something naturally constructed, but which is singular, you desingularize it, then hopefully the C1 is 0. The singularity not too bad. You don't add too many things. And too many things, then so the C1 is you don't create really C1 add divisors like a divisor. C1 trivial. So a Krapin such. In such C1 meaning C1 symplectic Calabi-Yau with required properties. So the link between hyperbolic geometry and symplectic geometry. So the link here was actually first noticed by Reznikov. I think the hyperbolic tracer space over hyperbolic space actually emit a symplectic structure. But here, to construct one with trivial C1, you need to start with something single orbifold. If you start a format smooth ones, you can now create this variety of Calabi-Yau. And actually, before this construction, even before that, I think this is around 2010. Yeah. People were interested in this question. So the question of whether there are symplectic Calabi-Yau 6 manifold, which is not Kähler, already interested. So particularly Ivan Smith and Richard Thomas and Yao, they attempted to use this a symplectic conical transition to construct such a non-Taylor example. I think it's around the same time we prove this. Prove the homological bound for symplectic labial surfaces. They introduced this is like earlier. Well, I mean, there's still it's still open question at the time. Construct Taylor. Symplectic coupling. 6. So by the way, yeah, I think here, the examples also could be taken to have there such. So they could also construct such some, these are big, right? There's a big symplectic labial with a big fundamental group, but they could also construct one with a small B3. But any Taylor labial manifold has non-zero B3, and in fact, Evan, Richard, and Yao wanted to construct one with 0 B3, and the constructor is very easy to describe. Actually, it's related to what I'm going to talk later, and also to Yuki's talk. So what is this construction? This is just to try to find a collection of Lagrangian 3 spheres. And you collapse them and replace by symplectic 2 spheres. So you see that here you reduce B3 at the expense of increasing B2. Of course, here just like here you need some homological conditions, like the sum of the Lagrangian spheres should be 0 in order to have a symplectic condition. So there is a similar conditions here you should impose to get a symplectic structure, right? It's just like in algebraic geometry, you want to construct a Taylor one. You want outcome to be Taylor, then you need some homological condition on the set of Lagrangian spheres being collapsed. So this is but anyway, this is a very nice construction, but and there are also other constructions simply by taking fiber sum even later. Just after 2010, there are more straightforward constructions by my colleague Hamelov. Use fiber sum construction. To construct along T4. Roughly. Well, the advantage of this construction is this is very straightforward. You're computing topological invariance, and you'll see that why you just stay in the smooth category, and then you see the C1 is 0. So really, you're summing along a Calabi-Yau surface. You start with like Fano to Fano pieces. You sum along a Calabi-Yau lower dimensional piece. You can get Calabi-Yau. So that the lower dimensional example of this is this fiber sum decomposition of a K3. The generalizing this. Of course, this construct does not give you a non-Kähler one. This is just the K3. I want to mention that the Usher studied all fiber sum construction of symplectic Calabi-Yau 4 manifolds, and what he showed that the fiber sum just does not give you any exotic, does not produce any exotic symplectic Calabi-Yau surface. So he showed that basically you construct K3 and Rick surface and some T2 bundles of T2 if you use fiber sum. But while in dimension 6, you can get something non-Kähler actually quite easily. So here just depending how you glue along the 4 torus, you have a freedom to choose the appropriate gluing map along the 4 torus. So if you twist the gluing, then you can get CY with non-Kähler type of Beatty number conditions. So, okay. And then here I just also want to say something about Fano or monotone two manifolds. So in fact, Fine the panel also constructed non-Kähler Fano or monotone or no, yeah. Your similar construction. With your space and taking resolution. And here, they can only construct complex 6-dimensional examples. So there are no 6-dimensional non-Kähler monotone examples. I think there's still no 8-dimensional, no 8-dimensional examples. Well, I wouldn't be surprised if there are such examples. On the other hand, they also conjecture in dimension 6, if you impose additional conditions on some symmetry conditions on a monotone 6 manifolds, then you should just get Kähler ones. So some of them specifically they conjecture that following the Hamiltonian S1 with Hamiltonian S1 action Kähler. Of course, if you impose the maximal symmetry, a 3-dimensional torus symmetry, you know it's toric, so hence it's Kähler, right? So you're saying that just any continuous symmetry, then there will you'll stay in the Kähler category. And this.
So in this construction, in order to prove that they are not non-Kähler, do they use usual criterion saying that the Hodge number are not have the symmetry?
I didn't check, but I think it's supposed to Beatty numbers. There's no Hodge numbers, but I didn't check the monotone case. I think probably well, don't quote them. Probably they can get something with a arbitrary fundamental group. Then you know some of them must be some of them must be non-projective because there are serious constraints on the pi one of algebra varieties. Yeah. So if they just get flexibility about the pi one, tells you some of them. So this is actually known if the action has isolated fixed points, or if B2 is equal to 1. So this is due to no. So maybe I mix up the definitions. So if okay, so if the action is semi-free, that means away from the fixed point, the action is free. So this is due to Chow. And or if B2 is equal to 1, this is actually a byproduct of this proved by Sugan-Tolman and stuff. In the paper, actually, that motivated by parking problems in dimension 4. That's the so this is probably the producer's talk on Monday, and also it's also known it is true. So what is also known, such Hamiltonian S1 monotone 6 manifolds are rationally asymplectic birational equivalent to P3, if that means something. So in other words, it can be obtained by blow up and blow down starting from P3 and a deformation. So this is a result of a Panoff and his former student. Okay. Now now I just make a one remark, and then I move to Uniruled surfaces. So, so the remark here is okay. Actually, the final varieties and Cabial manifolds of Cabial space are very important in algebra geometry. So the actually Bakar partly got his fused metal by extending Kolar, Miyauka, Morris abundance result for smooth final varieties. So Bakar proved that the final varieties with terminal singularities in each dimension form finite families. So this is the right. This is I think he proved it himself, right? This is after his work with Cassini and Hacken and Mackenzie. So he actually I actually asked Li Ren for help about this details. So he said that the argument is very complicated, very involved. The argument is very sophisticated, impressive, but he was able to show that the final variety, the terminal singularity, still have the finiteness problem. So this is very important because final varieties are like so we'll run the minimal model programs So so the final products are either NAF varieties, which are NAF, or final fibered varieties. Varieties of final fibers. Okay, it's right.
Just a little comment here.
Hey.
I think Kosher Burkhart's result is for epsilon log terminal. So epsilon away from log terminal.
Epsilon terminal. Yeah, you have to fix epsilon, right? So it's a I mean
You need epsilon away from log canonical.
Oh, okay. So that shows my my imprecise understanding. Epsilon terminal. Oh, log terminal. Epsilon log terminal. Oh, so you can. So Stephen, what's the precise category of singularity? Must be tau. I lost. Okay. Yeah. For some reasonable singularities, like related to terminal singularities, then you can establish this boundedness property, especially like the volume is bounded, the top power of canonical class is bounded. Okay, so let's
epsilon log canonical. It's a bit better than, stronger than that terminal.
in particular for terminal, right? Yes. So
log terminal. It's epsilon log terminal. It's called.
Log terminal.
Not log canonical.
Log terminal.
Okay. Or so I mean, for symplectic geometers, we don't understand the smooth ones, so let alone the singular ones. I'm not too ashamed of them because the smooth ones I still don't really understand. Okay, then. So we've seen this class of surface several times in the morning with this talk. So just to say something about the history, a little bit of history. So we, I think this is the first big result by Gromov about this kind of surfaces. So his assumption is that if omega is a symplectic structure on CP2, and it has a omega symplectic line. Actually, I don't need this. This means a symplectic submanifold in the class of the line. And then omega is standard. So omega here is not known to be Kähler, just arbitrary symplectic structure, but the assumptions you have a nice rational curve. And then you show that the result I mentioned before. So if M has a symplectic sphere, then M is either CP2 and omega standard or bundle Riemann surface point, and omega is root in the sense that there is S2 vibration on the four manifold such that omega, each fiber is symplectic.
Actually, so when the base is S2, this was proved by Gromov.
Oh, okay, yes.
Yeah. And when the base is not S2, it was proved by Megdaf and me. We classified our rules.
I will mention that. Like, yeah, I'm going one step at a time.
But then sigma, okay, but then sigma should be just a sphere in the
So it's sort of like a little bit history. I'm going slow. And then the it helps show that any omega CP2 that's this asymptotic. And then myself and Aiko Liu and showed that for these two class, these four manifolds, there always exists such a symmetry. And I think it's 1995.
approximately.
So, yeah. For manifolds that I'm just stating one property. I think you maybe in the paper you restrict to minimal cases, and then it's simple extension. So I did a simple extension and I to all such overlaps, just reduce to reduce to the minimal case. So anyway, this is okay, and then as many people contributed this, so anyways, I just don't know. So I just write again something about the space of symplectic structures. So the symplectic, for particularly the class of supporting symplectic forms. So this is has a very simple description. I think Paul is contributing to that. Paul Biran. So basically, let's prove this. And so this is saying that the symplectic cone for these four manifolds. And that in fact, this holds for the set of smooth spheres. This the right hand side is just completely topological data. It's just so it has very simple descriptions of this cone. We know what forms or what class can be represented. In fact, this is often it's convenient to present it as disjoint unions of subcones. So here K, what's K? K ranges over all possible symplectic canonical classes.
Sorry, you're allowing the area of the exceptional sphere to be negative as well?
Say it again, sir.
You're allowing the area of the exceptional spheres to be negative as well?
Yeah, it could be negative, yes. So yes, that's related to this decomposition. I'm going to write it down. So here I don't fix canonical class. Right? So there are many possible canonical classes, which are, and so I can write down the description for each subcone, and there we impose positivity condition. So these are the okay. So okay. First, what's the definition? This is description. This is the and the omega is required to be so here actually subtleties are here. I fix orientation. I fix the orientation of M. So that yeah, a fixed orientation. Then I can talk about B plus. Otherwise, I even cannot talk about B plus or orientation. Yeah. So here I require the symplectic forms to be compatible with my orientations. With a given orientation. All right. So this is the definition of this symplectic cone on this oriented four manifold. We can define this for a manifold arbitrary dimension, and it has this explicit description. And moreover, it decomposes into disjoint unions of spaces. So this is we get called symplectic cone, but in fact, it's not a cone. It's not convex. What is convex is the subcones. If you fix K. So here, this is the definition of this is that this consists of class of symplectic forms whose canonical class is the given K. This is definition. Okay. This is the definition. And here, and the description of this subcone is, okay. So it's in addition to this condition, so you require alpha on those E's, alpha is positive on the subset of this class of smooth spheres. So what the subset I call EKM or EMK. These are the class of smooth spheres such satisfy in addition, okay, that satisfy that junction with respect to K. So it's E dot K is equal to -1. And here I require positivity. And if so this is like, so we know cohomologous forms are symplectic, and we know which class can be represented by cohomologous can be represented by symplectic form. So we have pretty good understanding of the symplectic structures. touch space. Maybe I'll just keep here. And then the next thing. So it's okay. So next thing I want to talk about symplectic surfaces. Briefly. Yeah. Okay. By the way, so these. That's okay. Uniruled symplectic. Are the only all the format. Well, you see that this is from. If it's uniruled, it must have this symplectic sphere with non-isomorphic section. This must be one of those, and all of those are all uniruled. These always have a symplectic sphere, right? So these are exactly the class of uniruled, the format. And then I will talk about the several aspects of such uniruled symplectic format. So first of all, it's very easy to construct lots of symplectic surfaces. I'll give you a sufficient condition for a class to have a embedded symplectic surface. Very simple condition. Well, let's restrict to the ones for smooth. So let's look at the case with class of non-negative square. And the second condition is that A dot dot so if all these non-negativity conditions are satisfied, then there is a connected symplectic surface in the class A. It's a very simple condition. So and then you can calculate the genus by a junction formula. Well, of course, there are questions about uniqueness after isotopy of symplectic surfaces. And like for CP2, this is like a problem that's studied by many people, but especially by Sieber and Tian. They show that after degree 17, all symplectic surface, homologous symplectic surface in each degree are actually isotopic. It's conjectured to be, the isotopy holds for any symplectic surface, or all homologous symplectic surface, CP2. But it's just the technique is a pseudo-holomorphic technique. It's just now, I think still true, but when you look at Sieber and Tian's proof, you see that it's hard to go further. Okay, so next I want to talk about the Lagrangian surfaces. So of course a lot of people study Lagrangian surface Hamiltonian properties of Lagrangian surfaces in symplectic four manifold. You want to understand Hamiltonian isotopy classes. So Well, okay, but first of all, I mean, it's primarily for tori, Lagrangian tori, right? So, but if I just look at homologically essential. Then there are very few there are very few topological types. In fact, there's only one topological type. If you assume the Lagrangian surface oriented. The only so there are no Lagrangian genus 2 surfaces, no essential Lagrangian tori. This is very easy. It's a very easy fact. So in fact, this is true. So that's B plus. So I already noted that the B plus of such four manifolds is equal to 1, always equal. This is simply because higher genus essential Lagrangian surfaces themselves have a non-negative positive square. And being Lagrangian means the pair trivially with omega, which itself has a positive square. So there if you have a high genus Lagrangian surface, though you have two positive directions, that's impossible. So you can only have Lagrangian spheres whose self-intersections is -2, so it's that's possible. And in fact, there are lots of them, general lots. So I wanted to say that's actually well, and then the question is about when can spot Lagrangian S2s. Okay. There are obviously necessary conditions. Well, first of all, okay, subtraction -2. And of course, A has to be represented by a smooth sphere. So it turns out for Uniruled four manifolds, these conditions are also sufficient. Section spelling. I think it's correct. So this is independent proof by myself, Wei Wei and Xiaoshi Xin. So our initial proof actually used SFT, but I somebody feel here. by studying intersections of Lagrangian surfaces with symplectic surfaces, you need our original proof. I think the SFT probably can be avoided to prove this. I know the proof also use Francis and Duce's inflation. Because we sort of we show this for some symplectic forms, a small, and then we use inflation to propagate. Yeah, it's just inflation away from this Lagrangian surface. So because I can find symplectic surfaces away from Lagrangian surface using the minimal intersection property between Lagrangian surfaces and symplectic surfaces with non-trivial Grom-Witten invariants. And since I have lots of okay, so see this is also important. I have lots of symplectic surfaces. So there are a lot. Especially I can find using the minimal intersection property, I can find many such symplectic surfaces away from a Lagrangian surface. So if I already know the existence for some symplectic form, I can propagate. Okay, I can propagate the existence by inflating, by changing the class of the symplectic form through inflation, while still keeping the Lagrangian surface. So this, and then it turns out we can just do, yeah, this is no obstruction. Yeah. Okay, and then I want to, okay, here I mentioned another general result, not just restricted to Uniruled full manifolds. So if I just look at the set of classes of Lagrangian spheres on symplectic full manifolds. So I understand completely this set for Uniruled full manifolds. Set. So I give a name. A little lemma says that if b plus n equal to 1, then this set forms a root system. In the classical sense. In particular, this is a finite set. And satisfy the two conditions, or three conditions being a root system.
So you said that any two sets Lagrangian S2s in a given class A are all Lagrange isotopic. It's what you said, isn't it?
Isotope.
If you fix A, then all your Lagrange S2s in the same class A are all Lagrange isotopic. Did you say that?
No, I didn't say that. No.
Because it's hard, this kind of thing.
No, okay. What we can prove, actually, at least in the rational case. Okay, now, all right. Let's talk about uniqueness, right? Here's the existence. So I can maybe I just use the other board. I can talk about it. Okay, I can comment on that. We do know something about uniqueness, but it's not always homologous Lagrange spheres are not always isotopic. In fact, the first such example was discovered by Paul Seidel with a 5-point blow up, the monotone 5-point blow up. But at least, okay, let's talk about uniqueness. At least for rational four manifolds. What we know is homologous Lagrangian S2s smoothly isotopic. Again, this is I think so. This well, so this is the same paper with Wei and also in the same paper of Xiaofu. So, and we also prove something later on. We also prove something more. Okay, this is the first statement. The second statement that I proved with Jun Li, not the great geometer, Jun Li, or student, that the homologous the torality part of the symplectic morphism group. Again, this is for rational format. So acts transitively on the space of the homologous Lagrange spheres. And then, but there are non-Hamiltonian. But here, Hamiltonian isotopic is the same as a symplectic isotopic. In like the so this is discovered by Sino. So I think we recently we have a much better understanding when this can occur, when this non-uniqueness can occur. So this is very this is a rare situation, at least for rational format. So in fact, given a fixed the topological type M for generic choice of symplectic form, you actually have uniqueness after Hamiltonian isotopy. But only with very special family of symplectic forms, you have this non-isotopic. And also we know to what extent this the non-uniqueness is. Yeah.
I'm a bit confused. So what do you mean by simp H?
Oh, okay. This is the subgroup of the sim, which so subgroup is a homological trivial part. Yeah.
Trivially on the homology.
Yeah, trivial on homology.
On the homology. But then it's the same as for S2. So there is no flux for S2. Therefore, this, if you have so simp H acts transitively perfect, then it's connected, isn't it?
Well, we don't know this group is connected always.
Just it acts.
Yeah.
That's the point. That's the point. Because if
the torality mapping class group, it may not be connected. It may not be connected.
The second statement.
Yeah. So actually, when you know this group is connected,
Then you get
it.
Hamiltonian.
In fact, that's how we prove the generically generically uniqueness, because we understand when this is connected in fairly general situations. This is a recent work. Yeah. Okay, back to this is Lagrange. Okay, so then we call this. So then we call this a Lagrange root system. Lagrange system.
Sorry, by classes in this statement, what do you mean?
Which one? This one?
No, in the body or in no.
The one I just wrote?
Yeah. So there you write the set of classes.
Represented by Lagrange S2 for a given symplectic format. So this is a set in H2 MC.
Okay.
Okay, so particularly, well, you know, then there is just ADE type, right? This is a classical root, it's all classified as just ADE type. So you should imagine this. Well, this is connected to the ADE singularities. Okay, so all right, I think that's okay. That's next topic. All right, so I want to switch gear. So talk about the symplectic surfaces
Lagrangian surfaces and mentioned a bit about symmetry, this metamorphism group. I want to discuss finite symmetries of rational surfaces.
Sometimes the button gets stuck.
Okay. So what this means, finite group actions, symplectic actions on rational surfaces. So we have a just name. Finite group. I use terminology surface. Algebraic geometry. It really meant rational format. Faithful, effective. One. So in a complex category, such surface called just rational G surfaces. Well, there of course. So you're concerned with the holomorphic G actions. Oh, well, obviously, well, this is interesting concept, but I think probably the real motivation for algebraic geometers to study such G surfaces was to try to understand finite subgroups of the plane cremonal group. What's the plane cremonal group? This is the group of a birational equivalences of P2. All the birational transformations of P2, they form a group. It's called the plane cremonal group. And they want to classify all the finite subgroups. It turns out there is a bijection between finite subgroups of plane cremonal group with rational G surfaces. So they're for P2 considered birational transformations. Here it's considered honest group actions. Say again. Finest subgroup of the group you select surface with a blow up. You blow up the indeterminacy. I didn't quite look at it carefully, but this is a well classical. No, I think it should be easy proof. And this is so I just write down that so this is the motive. This is the motivation more than 100 years ago in the late 18th and 19th century of the geometry. So G, I allow G to move to vary here with fine. The standard notation is removal 2. And here, there, they work with algebraic closed field. So, but since I'm working just with this is the geometries, I just picked to be C. Okay, so this is the group of birational maps. So a lot is known about these finite subgroups. So well, actually, just give you a flavor. Well, let's actually look at the one-dimensional lowercase. So instead of P2, let's look at P1. We can ask this question for P1. Right, so what are the so there's a complete list. So you have cyclic group, dihedral group, P2n, and tetrahedral group, which is isomorphic to A4. Fourth ordinating group. Opposite. Isomorphic to S4. And not surprisingly, it's the Sahedral isomorphic to A5. These are the possible isomorphism type of the finite subgroups. Moreover, groups of the same type and order can constitute unique conjugates class. So this is complete understanding of the finite subgroups conjugates. 101.
This is just finite subgroups of SC2.
GL1. Yeah. GL or GGL or PGL PGL2. Homomorphic. Homomorphic.
Right, but if you have a finite subgroup,
That must be in the compact.
omega,
Yeah, it must be compact, yeah.
average omega, then you get finite SC2.
So so this problem has been this problem has been studied about over the years, and so there's some structure theorem about the finite subgroups, and Well, we can study this problem just from the symplectic point of view, independent of this, this, this connection with a plane chromoidal group. Well, the problem is that, here we don't really have such a nice relationship with symplectic birational maps of a P2. It's just, but we can just study the symplectic rational G surfaces themselves. We want. So let me state the well, first of all, there's a notion of minimality in this context. We'll try to classify the minimal ones. Okay, so the symplectic rational. Well, in fact, you can this definition makes sense for all symplectic four manifold with a finite finite group action. You say G manifold is set to minimal if there isn't any non-empty set destroying G invariant. So G invariant -1 spheres, symplectic manifold spheres. If you have such a collection of disjoint G invariant subsets, you can just blow down them simultaneously. So, okay, such that the blow down manifold is still a G manifold. This makes sense for arbitrary symplectic four manifold and a Weming chain. Show that except in the case M is uniruled, this notion of minimality agrees with the ordinary G. The non-impure. But for particularly for rational surfaces, you could have non-rational G surfaces. You can a non-minimal form rational surface, but and G action, but you don't have such a destruction.
With examples to think of.
Yeah. So, okay. Lots of examples in the paper, so I have to think of it. There should be okay. Let me first tell you for 2-point blow up. 2-point blow up. Any G action cannot be minimal. I can show you that. Maybe you can see how this notion works. So, but for already starting from a 3-point blow up, you already 4-point blow up, you already have minimal G action for example, especially like a evolution. So you think about like a conic bundle that interchanged so conic bundle where some spherical fibers, it has just two components, -1 spherical component, but the action interchanged the evolution interchanged the two.
But they intersect.
Yeah, but they intersect.
Oh, I see, okay.
So that's if they intersect, you cannot blow down them simultaneously.
Okay, so that's why you circle disjoints. Okay, very good,
Yeah,
very good.
yeah. So one theorem about such surfaces is this. So this is joint work with Yibin Chen, Wei Wu, a few years ago. Suppose M is CP2, example C n CP2 bar with n at least 3. Then M omega is G minimal. Of course, G has to be non-trivial. It's an action is effective, right? G's then there are only two cases. First case, the symplectic form is monotone. Well, then there's very limited number of M. It's just ends from 3 to 8, as we mentioned, as 6 possibilities. Or there is a standard basis, homological basis H, E1, E2, En. So standard is geometric, right? So first of all, there's lines. They're represented by spheres, and they're the self-intersection of H is 1, and the others are -1. They're pairwise orthogonal. So this such a base is called geometric basis. There are many such bases, but they're all related by diffeomorphism of M. So this is some sense this just up to the diffeomorphism group action. There's a unique such basis. But okay, but given this situation, we can find such a basis. Okay, such that in fact, we can require a little bit more just beyond this G action. So I sense yeah. So this condition does have nothing to do with G. Okay? This condition says that all right, this is the so-called the omega is reduced with respect to this basis. So this means omega En is the minimal of the symplectic area of the set of this set of spheres. Okay, this is the set. This set I used to describe the subcone. Okay, I mean all these. Okay, so standard basis. All right, so first of all, okay, the basis also means the EIs. Okay, this is the EIs are in this set. So particularly, they can be represented by symplectic manifold sphere. But the order, but they're chosen so the last one has the smallest area, and the next one has the smallest area for all those orthogonal to the last one. So you have this, and then this is right. This is greater than omega en minus 1. This is also has the minimal property, and so on. So this can be such a basis always exists, but it's not necessarily unique. Okay, but then the condition here, okay, the G minimality will force the next condition about such such a basis that we can find. So what's that? This is true, and here. And okay. Moreover, the area of all of them are the same, except the first one. And in fact, the area of the first one is exactly twice. Okay, so not necessarily twice. So this is true, and okay, this and omega h minus E1. This is like a fiber class. It's precisely twice of the area of EJ, where J is at least 2. So, in other words, the symplectic structure on a minimal rational G surface is very limited. Either it's monotone. Actually, the monotone case, you just have equality here. You just replace the inequality by equality, then you have this is like a degenerate case. Monotone case. So this is a general case. This is a degenerate case. But only these two cases allow minimal symplectic G actions. Okay, why I assume n is at least 3 here. Remarks is that where is a remark? When n is equal to 2, no minimal, no G minimal. I don't have time to sketch the proof. This is very easy to prove. And for the smaller ones, actually, we have pretty good understandings of finite group actions. So the smaller ones are just P2, S2 cross S2, or P1 times P1, or P2 blow up 1 point. So Wei-Ming Cheng wrote many papers about these manifolds. So he proved that particularly, okay, that a symplectic G action, a minimal, well, it's actually I think probably don't need a minimal here. G action is actually smoothly conjugate to a linear action. So it has very strong classification, really. It cannot prove any such action is symplectic conjugate to a linear action, but it proves a smoothly conjugate action. So we restrict to the case when n has at least 3. And this okay. And then okay, so this is the first result about the symplectic structures. Let me just mention one more result. Okay, this is called the symplectic dichotomy, and then I stop. So this says that the invariant lattice has rank 1 or 2. This rank 1, if 1 in the case that if rank is equal to 1, then n is between 3 and 8, and m is monotone. In this case, this invariant lattice is just the span of the canonical class. Well, the rank is at least 1 because the canonical class is always invariant. Like this is at least 1, but it's just 1 or 2. If rank is equal to 2, then n equal to 5, or n is greater than equal to 7. Stops. And there exists a minimal symplectic G-conic bundle structure. Yes, structure. And in this case, not surprisingly, the invariant lattice is span of the fiber class and the canonical class. Okay, I just stop here and I want to make a comment. This result you see, you can state it in algebra geometry. Just replace monotone by phono. And in fact, that's exactly what is proved in algebra geometry. They first have this dichotomy. They proved using equivariant Mori theorem. Equivariant MMP, they proved this. So now the symplectic dichotomy actually implies the projected dichotomy. Why? Because any projected rational G surface always gives you a symplectic G surface. Just by choosing Kähler form and averaging the Kähler form, you get a symplectic G action. On the other hand, you have a symplectic G action. You may not get a holomorphic G action. Because you can average a metric. You choose a compatible metric, you average the metric. And then you induce the invariant almost complex structure, but the invariant almost may not be integral. So in principle, there are more symplectic rational G surfaces than projected rational G surfaces. But even in this presumably broader category, we still have this dichotomy about the rank.
But there's no known example of a
No, there are no known example. I mean, like so you can come back to this small cases. So you know after smooth conjugacy, there and then another. So this is actually a very important step in this program. Okay, studying finite subgroups of chromonal group in algebra geometry. From there, you can deduce many structural results about the finite sub, like the action, homologic action of G on H2 and so on. So this is like a first basic step in our geometry. But we can prove the analog, I think, using relatively straightforward symplectic method. So the main point is we consider the area of omega on these EIs. So we just use these to control the behavior of G action. So I don't have time to show you, but this is I think compare probably, we don't even encounter any singularities. It's just a very straightforward symplectic argument, but it implies the basic structure theory in algebra. Okay, I stop here.
Wait, like, one way of thinking about this is understanding like rational symplectic orbifolds.
You can think that way. Yeah, I think yes.
But like
global object, right? Global.
yeah,
Global object.
yeah. Yes. But what?
But whose resolution, whose smoothest resolution is still rational. This is not so. Maybe you can have rational object for whose resolution is not rational. So here's the total space still rational. We'll have to use.
So, but what? Like, wait. If you, to really show that a rational surface is like algebraic or something like this, like you start with some curve, and then maybe you make itself a dissection number 0, and then you try and sweep out some sort of inflation thing or something like this. But if you try that with an
Equivalently,
if you just try that with an orbifold, an orbifold or something, what sort of goes wrong?
Well, maybe this is the question that Wei-Ming Chen can answer. He actually studied it.
He tried this.
He tried it from the orbifold point of view.
Okay.
He did. He also tried to generalize the Taub's equivalence in the orbifold category. So he actually used it. He actually used it to prove analog of the finiteness of the automorphism group surface general type. This is probably is well known, right? For surface general type, the automorphism group is finite, and then it's like a Gang-Xiao actually give an effective estimate in K-squared. So Wei-Ming Chen was interested about this question for symplectic surface general type. You want to understand, what any constraint on the finite group actions on symplectic surface general type. Well, he cannot prove it. It's this boundedness of the symplectic automorphism group. But what he can prove is something like, if in the case of a cyclic group action on a surface general symplectic surface general type, so that just means quadratic dimension is 2. Okay. Symplectic quadratic dimension is 2. This is just what I. He can bound the P in terms of omega and some data. So there's some progress in that direction.
Yeah,
But he proved it using orbifolds.
I'm sort of surprised. I don't know. It's just.
Okay.
I think it's just hard because I haven't thought about this. It's hard. I don't know quite what makes this so difficult. Like, why did Wei-Ming Chen struggle? That's what I'm trying to understand. But
yeah, he's expert. I mean, so why this is. So I'm not a person. Yeah, so here actually he studied very in detail. I didn't list the finite possible subgroups. There are a lot of things to study beyond this. What fixed points, then all these things is they're very detailed information. So I just know the errors estimate.
Do we know anything about like the gene variant symplectic cone?
Okay, that's another part, yeah, in this paper, yeah, in this paper, yes, he tried very hard, he really wanted to understand the equivariant cone. So I think we got something quite, but not exactly what we want. Okay, so I can find, just like Mark did, just I want to find the paper to see. So.
Which paper is this?
Oh, this is the JDG paper, symplectic rational G surfaces and the actual equivariant symplectic cones. The equivariance is even in the name of the paper. Maybe you can take a look at that. So yeah, this is so there's some nice actually preliminary results about equivariant symplectic cone, but there's some issue we cannot quite resolve. So we didn't really pursue to the end. We just stated a partial result about equivariant symplectic cone. Sorry, maybe I just we can just leave the question there.
I think perhaps we can
Wrap
thank
up.
the speaker again, and further questions can wait.
Sorry.